Check this out. We've got something really fun today. This is so amazing, man. Oh man, again? Let's warm up. By graphing this quadratic, we could just put this in our graphing calculators, look at the table of values, and plot those points on the graph, and we'd be done. What about those times when you don't have a graphing calculator? We could factor, and that would give us the x-intercepts. So for this one, there's a common factor of 2. Let's get rid of that first. And then factor the remaining quadratic here, x minus 1, x minus 3. That will give us our 2 x-intercepts. And we can put those on the graph. From there, we could tell that the vertex would be at x equals 2. We can plug that in any of these equations and find the y value for that. Keep going from there. We could also put it into vertex form. And the vertex form, not surprisingly, gives us the vertex. So for this one, we want to factor out the leading coefficient, who becomes our bouncer. Leave a spot, 1, 2, for the house guests, and leave the awkward uncle in the backyard. We're inviting this guy divided by 2 squared, so that would be plus 4 minus 4, brings along his negative friend. We use the bouncer to kick him out into the backyard. And minus 8. And then we can put these terms together and factor this. So 2 x minus 2 squared minus 2. And this gives us a vertex of 2, negative 2. So that would be down here. From here, we can also see that this quadratic is vertically stretched by 2. So normally it goes over 1 from the vertex and up 1. In this case, because it has a positive leading coefficient. Over 1, up 1. In this case, it goes over 1, up 2. Before it went over 2, up 4. And now it goes over 2, up 8. And of course it's symmetrical. So that's how our quadratic would look. (7.2) Graphing absolute value functions. Let's graph our most basic absolute value function, y equals the absolute value of x. I've made a table of values here. Let's take the absolute value of each x value here. 3, 2, 1, 0, 1, 2, 3. Let's plot those on this graph. 3, 2, 1, 0, 1, 2, 3. And that's how our absolute value function would look. Now keep in mind that before it was just a linear function, y equals x, and if you take the absolute value of it, it's still got this straight characteristic to it. How can we write an absolute value function without the absolute value sign? Well, we could square x and then square root it. So squaring would get rid of any negative if there was one. And square rooting would return us a positive value because we always take the principal square root. We could also think of what happened in the first slide, and that's when we graphed it, it looked like this V shape. Now when x is already positive in quadrant 1, then this line is just y equals x, and when it's negative in quadrant 2, this line is y equals negative x. So it might be possible to break it up into 2 pieces. In some cases, this might be simpler. We see here's just x, and this is just negative x. Whereas adding a squared and square root to some functions that are inside absolute value might get incredibly complicated. So when we break up a function into more than one piece, it's called a piecewise function. Now for our example, y equals the absolute value of x, it would just be y equals x if x is already positive, and y equals negative x if x is negative. Now you see that where x equals 0, it's not positive or negative. So we have a choice. We could give it to the positive or we could give it to the negative. And by convention, we give it to the positive side. We like to be positive. So we could rewrite y equals the absolute value of x as follows. Notice this is a set bracket, but it's only the left one. Do not close it with another bracket on this side. So I'm not just forgetting, it's not supposed to be there. So we can take the absolute value of any function, and it will just be, in a piecewise, it'll just be the function, wherever the function's already positive or 0, and we just need to multiply it by negative, where the function is negative, because then the negative and the negative function itself will become positive. And then we'll always have the positive value, which is what the absolute value is trying to get us. For practice, let's draw this piecewise function. First piece is x is less than 2, and it's just x plus 2. It means it had an x-intercept of 2, and it's got a slope of 1. And we don't have the point 24, but we can get infinitely close to it. And then we've got an x-intercept of negative 2, and all these points going down. So that's the first piece of our piecewise. The next is a quadratic, in between 2 and 5, including the 2 and not including the 5. So at 2, we plug 2 in here, we can see that it's equal to 0. And we have that point, so I'm drawing it closed circle on the graph. The next point, when x equals 3, would be negative 5. And when x equals 4, negative 12. And when x equals 5, negative 21. And we don't quite equal 5, so I'll put an open circle at 5, negative 21. And this is the part of a parabola that opened down, so it's concaving down here, something like that. And the last piece is y equals 5, so it's just a constant whenever x is greater than 5. So I'll put an open circle here, and then the flat horizontal line with an arrow. Let's graph the absolute value of this linear function. First, we'll determine the intercept, so let's do the y-intercept first. That's when x is equal to 0. And that's pretty easy. You can see 3 times 0 is 0, plus 1 is 1. The absolute value of 1 is 1. So the y-intercept is 1. Let's do the x-intercepts. That's when our y value is 0. And when I look at this, I'm taking the absolute value of this linear expression, and I'm trying to get 0. But the absolute value of 0 is just 0, so these absolute value brackets aren't doing anything useful. So we can just get rid of them, ignore them, because it equals 0. So it's just 0 equals 3x plus 1. Now do some algebra, and you'll get x is equal to negative 1 over 3. And that's our x-intercept. So I'll put that on the graph here. Now we want to sketch the graph, so maybe we want another point on this graph, like if I put in 1 here, then I get 4. Or I can use the slope of this linear line. The slope is 3, so over 1 and up 3. If I go to the negative side here, I've got, how about negative 1 for my x value? Plug negative 1 into here, I get negative 3 plus 1 is negative 2. And I take the absolute value of negative 2 and I get positive 2. So there's another point on my graph. And then I can say I go over 1 and up 1, 2, 3 to find that point. Or I could use my table, negative 2 times 3 is negative 6 plus 1 is negative 5. Take the absolute value and I get 5. Or you can put this in your calculator and look at the table of values and plot those on the graph. So that's how our graph would look. Now we want to state the domain and range. So the domain, we'll do this in interval notation, is any real number. And the range, Also interval notation, greater than or equal to 0. And the last part was rewrite this equation as a piecewise function. So we put our single set bracket here, and then we just rewrite this, whatever's inside the absolute value function, rewrite it right there. Put a comma. And the other part will be the negative of this. Negative 3x minus 1. Now we just need to figure out where was this function already positive. So if you look at the graph, if I looked at 3x plus 1, it would be this line here, or the right part of this graph. So that means that this part of my V shape was already positive and the absolute value sign wasn't doing anything to it. So that would be when x is greater than or equal to negative 1/3. And the other part is where it was negative. It used to be down here. I took the absolute value sign and made it positive. Now it's up there. So that would be when x is less than negative 1/3. Remember, I'm giving the 0 to the positive case here. We want to sketch the absolute value of this linear function, write the domain and range, and write it as a piecewise function. For this question, I'm going to start by graphing the linear equation without the absolute value brackets. So negative 2x plus 6. That means that it would have had a y-intercept of 6 and a slope of negative 2. So that would be down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1, like that. So this would have been y equals negative 2x plus 6. Now I can see that this part right here up until the x-intercept was already positive, and so I can just trace that. Nothing's going to change when I take the absolute value of that. It's this part here that's going to change, so 4 negative 2 becomes 4 positive 2, and 5 negative 4 becomes 5 positive 4. So this is the absolute value graph here. Now when you do this method, it's nice because then you can just make everything positive, and it will help you write it as a piecewise function. Just make sure to label the graphs or erase this original one here so you don't end up being confused. Now let's write the domain and range. So the domain is any real number, and the range is anything greater than or equal to 0. So remember, the square brackets means greater than or equal to here. Next, let's write it as a piecewise. Single set bracket. Don't close it, we just want the 1. The first thing, we'll just write the original function. Just whatever was inside the absolute value brackets. Don't change anything. And the next part, we want to multiply by negative 1. So this would be 2x minus 6 instead. Now, this part here was not changed. So it would be the part where we traced over the red line with the blue. It was already positive in this interval. We didn't change it. The absolute value sign was useless. That's when x is less than or equal to 3. And the other one is the part that we did change, and we have to multiply by negative 1 to flip it up here. That would be when x is greater than 3. Now some of you may have noticed I wrote if in this example, and in the last example I didn't write if. I just wrote comma and then the restriction. And either way, it can be understood that that's the restriction on the piecewise case. Now we're given the graph, and we want to take the absolute value of it. We're not given the equation. So first we want to draw the absolute value of f of x. Right here, f of x is already positive, and so nothing is going to change. It's this part down here that's negative. We want to make it positive. So this point here, negative 1, negative 1. Take the absolute value of it, it becomes negative 1, 1. We're not doing anything to the x coordinate, only the y coordinate. This one here, Negative 3, negative 2 becomes negative 3, positive 2. And this one, negative 5, negative 3 becomes negative 5, positive 3. And here we get our V shape. So there's the sketch of the graph. We'll say this is the absolute value of f of x. Next, write it as a piecewise. So y equals, this first part here has a slope of 1/2. It goes up 1 and over 2. So a slope of 1/2 x. It also had a y-intercept of negative 1/2. So that would be this part right here, or this old line here, and that's if x is greater than or equal to 1. Nothing's changed, it's still that. And now we want the negative one. You can see this has a slope of negative 1/2. It goes down 1 and over 2, down 1 and over 2, and it has a y-intercept of positive 1/2. We can get that by multiplying this equation by negative, or we could get it from the graph. And that's if x is less than 1. In this course, we only have to take the absolute value of linear and quadratic functions, so you'll never see something this complicated. But if we tried to take the absolute value of this function here, it wouldn't be a problem. So every point where you see it negative, we just need to make that positive. Okay, so this one would look something like this. Now this is already positive, and so we can just trace it. And now we're here, and this is negative, so we need to reflect it and make it positive. Now we're already positive, so we can just trace this. Now this dips negative, so we need to make it positive. So it looks something like, and last, that's already positive, so we're fine. And that would be the absolute value of that function. Now let's do the absolute value of a quadratic. First, we'll determine the intercepts. That would be the intercepts of this, not the intercepts of the quadratic that's inside here. So we'll find the y-intercept first. That's when x is 0. So if we put 0 in there for x, we're going to end up with the absolute value of negative 5, which is just 5. So our y-intercept is 5. Next we'll find the x-intercepts. So that would be when y is 0. And let's factor this to find them. X minus 5, x plus 1. That means that our x-intercepts are at 5 and negative 1. Those are the two values that will make this equal to 0. Negative 1 and 5. Most people like to graph the quadratic without the absolute value signs and use that to sketch the graph of the absolute value and also figure out the piecewise later. So I'm going to do that in red. I'm going to graph y equals x squared minus 4x minus 5. The x-intercepts will be the same. The absolute value of 0 is just 0, so those don't move. The vertex will be halfway in between the two x-intercepts, so at 2, plug 2 in here and I get negative 9. Put some other points in here for convenience in drawing this, so over to up 4, over to up 4, and how about 6, 7, and negative 2, 7. So here's my quadratic before I took the absolute value of it. Okay, and I'm going to label that y equals x squared minus 4x minus 5. That's not the question. I'm just using that to help me. So back to the absolute value. Wherever the graph was positive, I'm going to leave it positive. So this section right here, I can just trace it. That's positive. Same with this side here, it's already positive. So I can just trace it as well. That's positive as well. It's just this part down here. I need to flip all of these points up here so that they're positive. I've already got the y-intercept marked on here. So I'll just put the other points like 1, 8, 2, 9, and 3, 8, and 4, 5. So it should look like this. Now, when you're drawing these, if you draw y equals x squared minus 4x minus 5, your curvature will all be correct. And some people really have trouble. This is concave up, this is concave up, okay? And the middle part's concave down. So what I see students do is they draw it like this, and that's just not right. Okay, this is not concave down, Okay, and so drawing the original really helped to prevent this problem. Okay, no way. Now the domain and range of our absolute value function. Remember that this whole question is about what I've drawn in blue here, not what I've drawn in red. You're only using this to help you. So the domain would be x is such that x is any real number. And the range is y is such that y is greater than or equal to 0, and y is also any real number. Now I want to write my function as a piecewise function. So I will just write the first part, whatever was inside the absolute value brackets, and then I'm going to do the negative of that. Now, the first one is, wherever it was positive, it was this equation. So wherever I traced over the red here, it is just that. The absolute value signs weren't doing anything. So that would be x is less than or equal to -1, and x is greater than or equal to 5. And this other part where I had to flip it around, that will be where I had to multiply it by negative. So that's from -1 to +5. Let's graph another quadratic absolute value function. First, we'll determine the intercept. So the y-intercept, that would be when x is 0. That would just leave us with the absolute value of 30, so our y-intercept is 30. For the x-intercepts, that would be when y is 0. So let's factor this stuff. Negative x squared plus x minus 30. I dropped the absolute value signs because when I'm setting it equal to 0, they weren't doing anything. I also don't need this negative sign here. Just x plus 6 and x minus 5. That means our x-intercepts are 5 and -6. Now I want to sketch the graph. I'm going to sketch the graph of the quadratic without the absolute value sign first. It has the same x-intercepts and also has the same y-intercept. And then to get some more points, I'm just going to use the table of values off my calculator. Now that I've sketched the quadratic, I'll take the absolute value of it. So this part here, it's already positive, so I don't need to change anything there. I'll just trace over it. Next, these two legs, they're negative, so we need to make them positive. So that's how our graph would look. Next, we want to state the domain and range. So we'll do that in interval notation. The domain can be any real number, and the range greater than or equal to 0, and expressed as a piecewise. So we have y equals. Now, wherever I copied it, that's where it didn't change, so I can just use negative x squared minus x plus 30. And the other one, I will multiply by -1 to get this other part here. That would be x squared plus x minus 30. And where do those two things happen? This first one happens where I traced over it. And that's the benefit of drawing this quadratic without the absolute value sign, is that wherever I traced will be our positive case, wherever I didn't trace will be the negative case here, that I had to multiply by -1. So that would be from -6 to +5. And the two legs where I had to change this would be x is less than -6 and x is greater than 5. This was part of Relations and Functions 2, Graphing and Analyzing Absolute Value Functions. Here's some questions. Try them out, see if you know what you're doing.